Hello everyone, in this video I'm going to be going over the properties and different equations that we will be using for gases. There might be some more that I'm going to add on to this in later videos possibly, but for now we're just going to go over this stuff. It is going to be a fairly long video, but we're covering quite a lot in this. So first I just want to talk about what exactly a gas is. So as you can see in these beakers, I'm sure we all have learned this maybe in like primary school, you probably learned it in high school, but basically what a solid is it's something where the molecules are very tightly packed together, and because of that it holds its shape and form, right? That's why everything that we hold stays its shape, right? I'm holding a calculator right now. The reason why it's not spilling out of my hands is because it's a solid. It keeps its shape, right? And then we have a liquid, which actually forms to the shape of the container that it's in, right? So if you pour water into a glass, it just fills up the glass. You know, it doesn't stay a certain shape. It completely molds to that shape of the glass, right? You know, you can put it in a glass that's shaped like a star, and the water's going to be shaped like a star. You know, it's just going to fill that container. And with liquids, the molecules are slightly further apart and more energized, meaning that they can move around more than compared to a solid, but it's slightly less than a gas. And now talking about a gas, gases are molecules. Their molecules are very spread apart, and they have a lot of energy, so they're moving around, bouncing around. They can bounce off of things. They don't necessarily hold a shape. They are like free-flowing and free to float around, obviously, like depending on the density. Some gases are really dense and will actually kind of act like a liquid in a way, but they're still considered a gas because the molecules can free flow and move around. So those are kind of like the basic differences of those three things. I'm sure you can get a more in-depth video on it that probably explains it a little bit better than I just did, but that's the basics, right? So since gas molecules are so far apart, they can change due to the pressure, volume, temperature, and amount of moles present of that thing, right? They change a lot due to these things. You know, when you think of a solid, if you're changing the temperature, it's just going to get hot. Like, it's not going to, you know, create a pressure change if you change the temperature. You know, nothing crazy is going to be happening there. If you change the volume that a solid's in, it's not going to change anything unless you're crushing it and it explodes because you're literally crushing it. If you change, let's say, what did I just say? That would go along with pressure too. And if you change the amount of the solid, it's also not really going to change much because they're so tightly packed. They can't really get any closer or any further apart from each other. Versus a gas, they have a lot of room to move around. So if you increase the temperature, they can spread out even more, which will then impact the volume and the pressure of whatever it's in, and such like that. So this is where we can get all of these equations from. So now looking at those equations, as I said, because of this we get a lot of equations, and the first one and the most important one, and personally my favorite, is the ideal gas law. So the ideal gas law states that PV equals nRT, where P is pressure, V is volume, N is moles, or like the amount of something, and R is our gas constant, which we are going to be given, so that number does not change no matter what you're dealing with, right? It's a constant for every single ideal gas, right? And an ideal gas is something considered like non-reactive. Usually your noble gases are your ideal gases, right? They're not going to react with something. They're not looking around for an electron to react with and forming different bonds. So when we're using this, there's going to be a lot of times where we're assuming that something is an ideal gas, like oxygen. But oxygen technically isn't an ideal gas, and it'll vary a little bit different from this. But that's basically what we mean when we say an ideal gas. So in higher level courses, you might talk about the differences between an ideal gas and a not ideal gas and how those equations are different. But for right now, we're going to be assuming that everything is an ideal gas and there's nothing crazy going on. So with that being said, The next thing is the temperature, which is going to be in Kelvin. The reason why the pressure, volume, and temperature are all in their specific different units is because we're going to be using this specific R, where we have the unit is liters times atmosphere divided by Kelvin times moles. So that means that we need our things in atmospheres, liters, kelvins, and moles, right? So pressure is going to be in atmosphere, volume is going to be in liters, moles is always just in moles. You might have something in grams, and then you have to convert it to moles, so just keep that in mind. The gas constant always stays the same, that doesn't change. And then our temperature is going to be in Kelvin. So just some little notes here that we're going to be either given our stuff in atmospheres or torr slash milligrams of mercury. So if you have something in torr or in mercury pressure, basically, you're going to change that to atmospheres, right? And there's the conversion for that. If you have something in milliliters, which is very common, you're going to have to change that to liters. And there's 1,000 milliliters in 1 liter, so you're going to have to convert it that way. Our R always stays the same, where it's 0.08206 liter atmosphere Kelvin mole. And then we also know that Kelvin can be converted by adding 273.15 to our Celsius number, and vice versa. If you have something in Kelvin, you want to get it to Celsius, which in this situation we're not going to be doing that because we want our thing in Kelvin, you would just subtract. Okay, so just a reminder, PV equals nRT. Ingrain that in your head. We're going to have it on the test, like he's giving us a sheet, but best equation out there, not going to lie. All right, so let's do a question on that. Let me see if I can find the one that I want. Yeah, there we go. All right, so we have a 325 milliliter container of an ideal gas that has the pressure of 695 torr at 19 degrees Celsius, and we're going to find the moles. So I'm just going to underline the things that are important. Milliliter 19. Okay, so remember we have PV equals nRT. All right, so let's find our pressure. So our pressure is 695 torr, so let's do 695 torr, and let's convert that to atmosphere. So we know that in 1 atmosphere there's 760 torr. All of this I believe will be provided on the test. If not, I would look through his notes and see. Actually, I have his notes pulled up over here. Oh, this was not it, but yeah, so I would pull up his notes and see if that's going to be provided on the test. If not, write that on your card because that'll be important. So let's do that out. 695 divided by 760, and that'll give us 0.91. I'm going to go to 3 sig figs here, just for the calculations, and then we'll go and do it in 2 sig figs because we only have 2 sig figs here. And then our volume is 300. Oh, just write this. And then our volume is 325 milliliters, and we are going to divide that by 1,000 milliliters to get it in liters, which will be 0.325 liters. 0.325 liters. Alright, so now our moles. Alright, that's what we're finding, so we're going to leave that. Our R value is always going to be 0.08. Wait, let me just check and make sure I'm doing this right. Oh, wrong slide. 0.08. Okay, cool. That's what I thought it was. Just want to make sure I had the right number. 206. And then temperature is 19 degrees Celsius, so we're just going to add 273 to that. I'm not going to worry about the rest of the sig figs. So 273 plus 19, that'll give us 292. So 292. Alright, so now we're just going to bring this over, all this, 0.08206 and 292. 10826 292. And we're going to do that out in our calculator. So we have 0.914 times 0.325. We're going to divide that by 206. This should be a 206 times 292. And we will get 0.02 moles. And I'm going to see, let me check and see if that was a question on here. Yep. Oh, I forgot to round up. Well, I didn't round up because we only had we only had 2 sig figs. Not sure why we went to 4 there, but this would be your answer there. Cool. So let's move on and talk about static versus dynamic. So static versus dynamic. So what dynamic is something that changes, right? You can think of it as, I don't know, I feel like that's a pretty used term, but dynamic is just something that changes and static is something that stays the same. You can think static stays the same, like the S's are together if you need to memorize it. Static stays the same, all S's, right? Just came up with that in my head. For these scenarios, we use P1V1 divided by N1T1, and the 1 just represents like your initial, so you can say PIVINITI if you want to, whatever works for you. I prefer using the 1 and 2 just because like this is like the first phase of it and that's the second phase, but that's my weird way of doing things, I guess. And you're going to set that equal to P2V2 divided by N2T2. This is actually derived by setting 2 PV equals nRT equations equal to each other. So if you were to divide this to make sure that we get R by itself, you would just get PV divided by NT. And since R is a constant, we can set those two equal to each other, and that's why we get this. So some examples of static versus dynamic. Let's look at a static question, so something that stays the same. This says, what is the pressure in a 2-liter balloon at 23 degrees Celsius with 50 moles of gas present inside? Very similar to the last problem that we did. Nothing is changing. We're just asking simply, what's the pressure of this scenario? Versus the next one, it says, what is the final pressure in a 2-liter balloon after it is heated from 23 degrees Celsius to 50 degrees Celsius with an initial pressure of 2 atmospheres? 2 moles are present inside of the balloon. So as you can see there, that's something that's changing, right? So you have a final pressure, initial pressure, you have a temperature change in there, lots of things are changing, so that would be something that is dynamic where you would use this equation. So let's do an example problem on that. Let me see if I can find mine. Is this it? No, that's not it. There we go. All right, cool. Found it. All right, so, I actually made this one up, so I hope it works out and makes sense. A can of soda is shaken a lot. If you guys know, when you shake a can of soda, it explodes, building up pressure from the carbon dioxide escaping. If the original can had a volume of 100 milliliters and a pressure of 1.2 atmospheres and 0.7 moles of CO2, after shaking, the can had 20 moles of CO2, so there's that CO2 escaping, and we're assuming that there is no, we're looking for pressure. Forgot to write that. That's what happens when you write your own problems. Assume no volume change or temperature change. All right, so we're not even going to worry about this volume. So we're going to say screw this volume because you're not changing. And we're going to use PV, so 1, N1, T1. And because we can say that the volume is not changing, we can actually take it out of the equation, and also the temperature is not changing, correct? No volume or temperature, so we can take that out of the equation. So let's set that equal to P2, V2, N2, T2. Again, we can cancel those out, which will just lead us with the equation of P1 over N1 is equal to P2 over N2. Cool. All right, so let's see what we got here. We have the pressure. All right, everything is in the units that we need, so we can just plug it right on in, which is awesome. All right, so the initial pressure is 1.2 atmospheres, and the initial moles is 0.7 moles. Oop, not multiplying, my fault. All right, and that's going to equal 20 moles, and we don't have that final pressure, which is what we're going to find. Okay, so now all we have to do is just multiply that by 20 and this by 20. So we'll get 20 times 1.2 divided by 0.7. This will give us a P2 of 34. Let me see. Okay, I can really only go to one sig fig, but I'm going to get a 2 here. Atmospheres. That's pretty. It's a lot of pressure. This problem was definitely not written out the way it should have been, thanks to me. But yeah, that thing would be exploding quite a lot. Like yeah. You have a massive explosion on your hands at that point, honestly. Like, run. So yeah, so that problem's all worked out. Alright, so we just went over dynamics, so now let's talk about in reactions. So when we're dealing with something like a reaction, this is just something to keep in mind. I don't have a practice problem on this. I actually have a practice problem towards the end of this video that we'll discuss. We're going to be using stoich in order to determine amounts made or used. So just a reminder of stoich, we use mole conversions, and that's basically what stoichiometry is. It's really just all mole conversions. So I have an example here talking about cars, because I love that example. You have 4 wheels and 2 doors and 1 engine, and that's how you make a car. So that's the reaction, and we say with 36 wheels, how many cars can be made? So we start with what we're given, which is 36 wheels, we divide that by 1, and then we multiply that by the mole conversion. So we're going to cancel out the wheels, so we're going to put wheels on the bottom, so we can cancel those out. And we want our cars on the top, because that's what we're looking for. So we do that math out, and we get 9 cars made. You're also going to be possibly doing some gram conversions, so you just do moles to grams, which we've done plenty of times, so hopefully that's really easy for you guys. You just use the periodic table and just do a mole conversion. And you're also going to be using PV equals nRT, right? So we're going to be finding moles to get our N there, right? You know, we're not going to be using stoich to find the temperature or to find the pressure or the volume, but we will be using it to find the moles, and then from there we can find the rest of those components. So that's just something to keep in mind. Moving on, we have gas mixtures. So when gases are mixed, they tend to have their own certain pressures because they're different gases, and they tend to have their own mole fractions, right? So if you think of something like this, right? If you have a classroom full of people who were told to wear red shirts versus people who were told to wear green shirts, this is so random. A mole fraction is kind of like determining how many people are wearing green shirts out of the total, and then how many people are wearing red shirts out of the total class. And it's kind of like similar to a percent in a way. It's just telling you, here's how much there is of this thing compared to everything else, right? So that's a fairly simple concept, but we can find those mole fractions, and because we find those mole fractions, we can determine the amount of pressure each gas has in a gas mixture, right? So the equations that we're going to use for this is x sub I is equal to n sub I divided by n sub t. And we're also going to use p sub I is equal to x sub I, which these two x's are the same, keep that in mind, is equal to x sub I and p sub t. So the x sub I is the mole fraction, where it is in between 0 and 1. So it can't be less than 1, and it can't be greater than 1. And then Ni is the moles of I, and I said that I can be a subscript for any element, right? So if you're asked for moles of neon, it can be written like this, N-E, so that you know that's what the I is, right? And then the moles total, you would just add up all the moles together, and that would be your moles total. The pressure of I is the pressure of a certain element, so again, you could do PNE if you're using neon, and then PT is the total pressure. So those are your gas mixtures and those problems. I believe that this one is a gas mixture problem. All right, great. So a mixture of helium and neon has a total pressure of 1.32 atmospheres. It contains 0.74 moles of helium and 0.89 moles of neon. What is the partial pressure of helium? Okay, so we're looking for the partial pressure of helium. So I want to find first the mole fraction of helium, so HE, and that's going to be equal to, again, our moles of HE and then the moles total. So the mole fraction of helium is going to be, where's helium? Helium, we have 0.89 moles, and then the total is going to be 0.89 plus the 0.74. And we do that out in our calculator. HE, we're going to get 0.9, and then 0.9 plus 0.74. You will get 0.55. Okay, so now moving on, in order to find the partial pressure, remember we're going to use the equation PI is equal to, well, I'll change this to helium for us. PE HE is going to be equal to the mole fraction times the P total. I'm just going to recheck the equation because I don't have that one memorized. All right, cool. So I guess I do have it memorized because I did remember it. So the pressure of HE is going to be equal to that, this thing, what's the word for it? Mole fraction, there we go. And then we're going to multiply that by the total pressure, and we will get 7.2 atmosphere for HE, and that would be your answer. Okay, so that's all for kind of like the lecture portion of this, I guess. Now I'm going to get into some practice problems. So I have one fairly easy practice problem, then I have one that's really hard that I kind of have multiple steps in it, so that'll be the challenge one. If you can do that, I believe you can do any of these. So the first one, a balloon has a volume of 4 liters at 44 degrees Celsius and 729 torr. What temperature must it be cooled to in order to reach the volume at, okay, so that's the volume that we're trying to get to is 3.78. Assume that there's a constant pressure. Okay, so this is going to be a question where we're going to be doing that dynamic versus static, right? So if we remember that, it's going to be, let me just get it down right so I don't mess anyone up. Okay, yep. So we have P1, V1 divided by N1, T1. We're going to set that equal to the same thing, but for the second part. All right, and it says that we're assuming constant P, so we're going to cross those bad boys out, and we're just going to get V1 over N1, T1 is equal to V2, N2, T2. Cool. Okay, so the balloon has a volume. We don't have to do anything with that, which is awesome. So let's write that down. The volume is 4.39 liters. And we're gonna do the, oh, okay, so I'm gonna assume that we also have the same moles. Assume constant pressure. Okay, so yeah, I'm gonna assume that we have the same number of moles here because there's nothing talking about moles here, so yeah, I'm going to assume that it also has the same number of moles. So the equation will actually be V1 T1 is equal to V2 T2. Makes things a lot easier. And there's a constant pressure, so we don't have to worry about this guy. I didn't feel like converting that either way, so that works for me. 273. So right now I'm going to be converting the degrees into Celsius, or degrees into Kelvin, 273. Oh. All right, and we get 317, and that's going to be set equal to 3.78 liters. And we're going to find that temperature. All right, so 317 Oh, that's not what we're doing. Okay, yeah, so let's do that out. We have 4.39 divided by 3. Divided by 317. And this over here is going to be 0.0138. Yeah, is equal to 3.78 liters. T2. I'm going to multiply both by T2. Alright, so we can cancel that, and then I'm going to actually divide this by 0.0138, and then divide this by 0.0138. So we get 3.78 divided by 0.0138. And we will get a temperature 2 of 3. For some reason I feel like I did something wrong here. I'm going to have the volume of that at that temperature. What temperature must be equal to? Okay, so I'm going to say that this is times 10 to the second. Something about that seems wrong. The reason why I'm saying that is because I feel like in his problem he got 0. Yeah, 0 degrees Celsius. Okay, so I just figured out why he says 0 degrees, because he said 0 degrees Celsius, because 273 degrees Kelvin is equal to 0 degrees Celsius. So, these can be your two answers. I was really looking at this and I was like, how did I mess it up so bad that I got 273 instead of 0? But yeah, so that is correct. And that's the reason why he wrote 0, because, yeah. That's funny. Yeah, so definitely check that, if you get an answer like that. I mean, that answer is also correct, but if, like, on the answer sheet it says 0 degrees Celsius, don't panic. Just convert. Alright, so now this is the tougher question here. Alright, so we have a balloon. I made this up, so it might also be another weird number that makes no sense because I made it up. A balloon is attached to a beaker where this reaction is occurring. So you have a solid thing of glucose and you're heating that up, and we're going to get 6 moles of CO2 produced. This is your cellular respiration that happens in your cells, where 50 grams of glucose react. Oh goodness, grams. Okay. The balloon begins at 300 Kelvin, 0.5 moles of CO2, and 0.5 liters of volume, and 1 atm. Then goes to 400 degrees Kelvin, 5 atm, 2 liters in volume. What is the pressure of the balloon after the reaction? So there's a lot going on in this one. But what I always like to do when there's a lot going on, this is more kind of similar to like a physics problem where you have a lot of things going on. Usually on Professor Sherlock's test, he kind of makes things fairly simple where, you don't have to sit there and do a ton of math because he really wants to assess you on your chemistry. But I think that this is a really fun one to test your skills in your chemistry equations. But yeah. So right now, my plan of action is to get the moles of this, because this is what's going to be affecting everything down here. So I'm going to have to find the moles of that first, and then I'm going to have to do this, right? So we're going to assume that there's one glucose reacting because it doesn't give us a script, right? So we're going to do 50 grams. I didn't give you the molar weight of glucose, so let's look that up together. Oh my god, that's so funny. I was trying to figure out what Doja Cat was saying in that song. So I was like, there's no way she's saying actual words. That's hilarious that just came up. Glucose molecular weight. Alright, so we get 180.156. So molecular weight is equal to 180.156. Let me just make sure I wrote that down right. Okay. So, we're going to say, I'm just going to call it like a big G for glucose, I guess. Let's convert that. So we're going to take the grams, and now let's find, we're looking for moles. So we're going to divide this by 0.156 grams of glucose. So we can now cancel out our grams, and we're going to get our moles, which is exactly what we want. So we're going to do 50 divided by 180.156, and we will get 0.278 moles of glucose. Okay, cool. So now that we know, oh, not moles of glucose. Oh, yeah, we are looking for moles of glucose. I'm so silly. Okay, but now we have to find the moles of CO2. So what we're going to do is we're going to say 2.78 moles of glucose. Divide that by 1 because that's our given. And we're going to do our mole conversion. So when we react 1 mole of glucose, we get 6 moles of CO2. So that means that in this reaction, we are going to make 1.67 moles of CO2. Finally, we have our moles of CO2 that we need. Awesome. So now what we can do is we can do this equation. And this is going to be an equation of, because it's changing, P1, V1 divided by N1, T1 is going to be equal to P2, V2 divided by N2, T2. So I don't believe there's anything in here that is static itself. So I think everything's changing, so we're not going to cancel anything out. So our initial pressure is 1 atm, and the volume is 0.5. Our initial moles is 0.5 of CO2, and the temperature is 300 Kelvin. All right, now we're going to set that equal to the ending pressure, which is, all right, so that's what we're looking for. Should have underlined that. What's the pressure? The volume is going to 2 liters. We're going to divide that by the moles that we found, so the 1.67, and the temperature, which is going to 400. Okay, I hope this one works out. So I'm going to find this whole thing first. So we're going to do 1 times 0.5 divided by 0.5 times 300. And here we're going to get 3.3 repeated times 10 to the third, negative third. Lots of 3's in that one. That's fun. And then here what we're going to do is we're going to do, we're just going to make this P2 with 2 multiplied by 2, and I'm going to do the math on the bottom. You can do this whichever way you want to algebraically. I tend to do things a little bit funky, so if you're watching this and you're like, what are you doing, Miss Ma'am? I do things weird. So this will be 668, and what I'm going to do is 668 and 668. That was horribly written. 668, we're going to multiply those together, so then we'll get P2 times 2 is equal to this, so times 3.3 e negative 3, and then this will end up being 2.2, yeah, 2.2 basically, and then we're going to divide this by 2, divide this by 2. So now we get 2.2 divided by 2, and this is going to be P2 is equal to 1.1. I'm just going to run through those one more time just to make sure I did all of that correctly, because the number's a little bit questionable, but again, I made up this question on my own, so I can't check it with anything, which is great. Love when that happens. 6, 7, 400. Divide that by 2. Yep, that's what I got. All right, so that is the answer for that one. So that is all of the questions and everything that I have for this video. I know it was very, very long, but I think that is a very worthwhile video with a lot of good information and some pretty fun practice problems. So I hope you all enjoyed, and I hope this helps, and thank you all for watching.